Welcome everyone to 2.1. This is derivatives and rates of change. The claim is we got distracted, right? In 1.4 we brought up this great idea, of tangent lines and slope at a point. But then we saw in order to calculate these things we needed this notion of limits. And so for the rest of chapter 1 we studied limits. So that way we can actually apply these to our good old slope at a point. So now the claim is it's time to finally go back, and now that we have all of this limit knowledge, we can apply it so that we can formally calculate out this tangent line, slope at a point, instantaneous rate of change, all that great stuff. All right, so let me do a little bit of reminder here before we get into the formal definitions and stuff. So we saw something like this from 1.4, right? So let me go ahead and hide the secant line stuff. Our goal was to calculate out the slope at a point. So at this time I have my nice function here, this blue function, and then I have the point picked out 4. But you can choose any of these, right? So any of these we could get slope at the point, but I wanted to do 4 for right now. Let me see if I can get back there. And maybe not. Let me go ahead and just type it in. There we go. So if I wanted to get the slope at a point, right, we claimed that this tangent line here was close to the secant line, where we pin one of the points at that 4 value, right? We want the slope at 4 in this case. And then the other one we move, and we get closer and closer to 4. And we can see when it's happening, we can see that the slope of this green line and the slope of the purple line are very, very close. Now if they were actually equal, right, the slope would be undefined, because both of them are the same point here. If you continue a little bit beyond that, again, you can see it's still close, right? The slope is close to the purple line. Here, the slope of the green line is close to the purple line. So this is what led us down this path of limits, right? We wanted these 2 points to be very, very close to each other, but not equal to each other. All right, so that is going to give us our definition for this thing, the slope at a point, which we're going to be calling the derivative. So the derivative of a function f at a number c is going to be denoted by f prime of c. So it's f of c with a little prime, kind of like an apostrophe right there or something. This is the number. F prime of c is equal to the limit, and we're going to let x go to that value c. And then we're going to do the average rate of change between these things. So f of x minus f of c divided by x minus c. So again, if we were to look at my graph, my c value is 4. This is what I want the slope at this one point right here, aka the derivative of this point, 4. And we're going to let this other value, which this would be our x, we're going to let it get very, very close to 4, right, using a limit. Not quite equal, but very, very close. Because if we do that, again, the slope of this green line, this average rate of change, should be very close to the slope of the purple line. And so that's why we have this limit here as x goes to c. Again, very, very close to c, but not equal to it. So then we're not dividing by 0 technically. All right, and this is, of course, well, limits, they don't always have to exist, right? So it turns out some derivatives don't exist. But if the limit exists, well, we say that the derivative exists. An equivalent formulation, the claim is this one's actually used a little bit more often. So the derivative at c is equal to, and then you use the difference between h and c. So the difference, we want that difference to go to 0. And so this is going to be f of c plus h minus f of c divided by, and really this is c plus h minus c, because again it's an average rate of change. But now notice that we have a positive c and we have a negative c, so those nicely cancel out and you're just left with h on the bottom. So again, this is an equivalent formulation. They'll give you the same values. It's just kind of things going to 0 is sometimes a little bit nicer, but we'll get a little bit of practice. You'll see in your homework about calculating out both of these. All right. So if you can calculate out this slope, right, this slope at a single point, or the instantaneous rate of change, then we can combine it together and make a tangent line. right? Which again, we brought up in 1.4. So the tangent line of the graph, y equals f of x, at the point c f of c, is the line through, again, c f of c, whose slope is equal to f prime of c, the derivative of f at c. And then, well, if we remember good old point-slope form back from our algebra days, we can actually write down an equation for this tangent line. And so the good old point-slope form goes something like, right, y minus the corresponding y point, so f of c, is equal to slope times x minus the corresponding x point. So here's the x point, here's the y point. And now the slope, we said we want the slope to be, well, this derivative thing. So f prime of c, so this is going to be f prime of c. And that's going to be an equation for a tangent line. And actually, if I go back to my pictures here, let me take off the secant line for a second. But actually, when I coded this, if I go under the tangent line, right, there's been this little arrow here that we can extend, we can see that I've actually had this code here the entire time. So this is y minus f of c is equal to f prime of c times x minus c. And so if you take that off, the tangent line goes away. So that is the equation for this tangent line right here. All right, let's get a little bit of practice using this definition. So I'd like to calculate out the derivative for a specific function, here it is, at 3. And so actually, just staring at this, the claim is we should be able to figure out what the answer is. But I want to get a little bit of practice, again, using this definition up here. So let's use that, and then I'll tell you how we can kind of verify our work for this problem specifically. All right, so I'm going to go ahead and use the second definition here. So f prime of c is equal to the limit as h goes to 0. Like I said, I'm going to use the second one, the one that's actually used a bit more. So the limit as h goes to 0 of f of c plus h minus f of c divided by h. And now in our case, our c value here is 3, right? I want to figure out the derivative at 3. So this is going to be f prime of 3 is equal to the limit as h goes to 0 of f of 3 plus h minus f of 3 divided by h. And so you can see in order to calculate this out, I'm going to need f of 3 plus h, and I'm going to need f of 3. So, okay, f of 3 is not so bad. F of 3 is equal to, well, it's just you plug in a 3 everywhere you see an x. So this is going to be 6 plus 5 equals 11. And then f of 3 plus h, this is a little bit nastier, but I'm plugging in a 3 plus h everywhere I see an x. So this is going to be 2, 3 plus h's plus 5. And so let me take one more line here to simplify this down. So this is going to be 6 plus 2h plus 5. Actually, even one more. 11 plus 2h, combining like terms. All right. Now that I have those values, let me go ahead and plug them in. So again, the derivative at 3 is going to be equal to the limit as h goes to 0. And now instead of f of 3 plus h, I'm going to plug in 11 plus 2h. And then I need to subtract away f of 3. f of 3 was 11. All of this divided by h. And so now we can see this plus 11, this minus 11 kind of cancel out. And so I'm left with the limit as h goes to 0 of 2h divided by h. And now again, if you were to just plug in 0 everywhere you saw an h, right? If I tried to use this direct substitution property, I would get 0 over 0, and that would be a problem. But luckily, there's an h both on top and bottom, so I can use this cancellation property to go ahead and cancel those, and I know that I would get the same limit. So now the limit as h goes to 0 of just 2, well, there's no more h's left. So this in case is just 2. All right, so that is my final answer. That is the slope at that point, the slope at the x value 3 for this function. And I told you, actually, for this equation right here, we should actually be able to figure it out because this is just a straight line. So I know it's a straight line with slope 2 and y-intercept 5. 1, 2, 3, 4, 5. And I'm just going to do a pretty crude sketch here. something like this. And so if I go over 3 and I ask you what is the slope at this point right here, well, actually for, a straight line like this, the slope is always 2. Whether you're asking about the slope at 3 or the slope at 4 or the slope at 5 or the slope at negative 100 or whatever, right? For a straight line, the slope is always 2. So in this case, again, because of this 2x plus 5 right here, we knew that actually the slope should be 2 at this point. So this is a slick way to be able to verify, but unfortunately it only works on straight lines. All right, but again, this was some practice using this definition of the derivative. All right, and that's it for this first video. I'll see you guys next time. We'll do a few more examples and applications of the derivative. I'll see you then.